common scenario that we have to deal with when we're looking at forces is when forces show up on a ramp. And what we're going to do with this is we're going to adjust how our x and y axis looks. So traditionally we have a y-axis that is pointed upwards and a horizontal axis or x-axis that is pointing to the right. Now, when we look at this, if we draw all our forces for an object that is on a ramp, we're going to say this is my force of gravity. We'll say my normal force. And really, if there's no friction, these are the only two forces that are acting. Now you could say, okay, well, that's not bad. Gravity's in the y direction. Normal force, though, is at an angle, so we got to deal with that. But what we need to understand is that the motion of the box on the ramp is going to follow this blue line. It's going to be horizontal or parallel to the surface of the ramp. So instead of dealing with things up and down, left and right, what we're going to do is we're going to redraw our x and y axis to have this be the y direction, and then down the ramp is going to be the positive x direction. So in doing that then, we're going to see that my normal force is in the y direction, but now gravity is actually at an angle. And so what we're going to do is we're going to break gravity up into its x and y components. So this would be the vertical component or the y component. This would be the x component. So this would be my force parallel. And we say that because it is actually parallel to the surface of the ramp. Whereas this component then we're going to call force perpendicular, because that is going to be perpendicular to the surface of the ramp. And what's really nice about this is that whatever the angle of my ramp is actually, if we look at the geometry, that's going to be the same angle here. So what I can do then is I can break my x or my gravity into its y component and its x component, which is just what we call the parallel component and the perpendicular component. If we wanted to do that, if I wanted to find the parallel component, I would simply look that, okay, I know my gravity is my hypotenuse. This is my opposite side. So if I look at SOHCAHTOA, what I can see is if I want the opposite and the hypotenuse, that's going to be sine. So I'll set that up that the sine of theta is going to be the opposite, which is my parallel force, over my hypotenuse, which is the force of gravity. And then if I multiply each side by the force of gravity, I can see that my parallel force is equal to the force of gravity times the sine of theta. Doing the same thing now for my perpendicular force. Because the perpendicular is the adjacent side, I'm going to use cosine in this case. So the cosine of theta is going to equal my perpendicular force divided by my force of gravity. Again, I would multiply each side by the force of gravity, and I would be left with that the perpendicular force, is equal to the force of gravity times the cosine of theta. So this is how I would break my gravitational force into its x component and its y component. Then, if we're looking at that, and we say, okay, now let's do the sum of the forces in the x direction and the sum of the forces in the y direction. In the x direction, then, I'm simply going to have my parallel force equals mass times acceleration in the x direction. In the y direction, then, I'm going to have my normal force minus my perpendicular force equals mass times acceleration in the y direction. Now, in the y direction, almost always my acceleration is 0. When we're talking about the motion down the ramp or up the ramp, we're talking about the motion in the x direction. The y direction, then, is not going to have any acceleration. And so what we can see, then, is that my normal force, my normal force would then equal my perpendicular force in this scenario. So whereas normally, if we just have that object sitting flat, right, my gravitational force and my normal force are going to equal each other. But now our gravitational force, some of that is going to be pushing down the ramp, which is our parallel. Some of it is going to be creating the force pushing onto the surface of the ramp, which that is our perpendicular. So that's how we'll break things up in the forces on a ramp. Now, what are some scenarios then that might come up with this is if we have our ramp and if we have our object that is sliding down, right, without friction. In that case, we simply have gravitational force and we have our normal force. And again, we're going to break our gravitational force into its x and y components. So this parallel force is causing it to accelerate down the ramp. Now, if we have that same object go back up the ramp, right? Now what we're going to see is if we're going up the ramp, we still have gravity pointing straight down, normal force pointing perpendicular. But now when we break that gravitational into its parallel and perpendicular, now this is actually causing it to slow down. So this parallel component here is causing it to slow down because we're actually moving up the ramp. And so in this case, what we would typically say is that this is the positive y. Typically down the ramp is the positive x. So for this one, I would have a negative velocity and my acceleration would be a positive acceleration. And remember that if those two are in the opposite direction, then I would be slowing down. With this one here, if I would have positive y, positive x is down the ramp, I would have a positive velocity and I would have a positive acceleration, and that's what would cause it to speed up. If we look at this then with friction, what would my force diagrams look like? So we'll go down the ramp, and then we'll go back up the ramp, and just see how things compare. So again, here, we have an object, it's moving down the ramp, but it has friction. So this is with friction. Now this case, we would have gravitational force straight down, normal force perpendicular to my surface, my perpendicular component, my parallel component, and I would also have a frictional force up the ramp. Here now, I'm moving up the ramp. Gravitational force would be straight down, normal force perpendicular to my ramp, break my gravitational force into the y and x component, and I would also have a frictional force here pointing down the ramp. So you just got to make sure you're paying attention to which way your x's and your y's. In this case, let's just do the y components are pretty straightforward. Let's do the sum of the forces in the x. What we see here is we'll say down the ramp is in the positive x direction, and we'll say, again, this is parallel component, this is force of friction. And so what we see is that the parallel component minus the force of friction equals my mass times my acceleration in the x direction. That's for this. Here, again, we'll say down the ramp is the positive x direction, whereas in this case, sum of my forces is we have our, again, parallel is right here, force of friction is right there. So we have the parallel component plus the force of friction equals mass times acceleration in the x. So what we can see here is actually pretty interesting that with friction, our acceleration down a ramp is going to be smaller than our acceleration up the ramp. Now this means that we're slowing down faster here than we would here. And that's because in this case, parallel and frictional force are canceling each other out, Whereas here, parallel and frictional force are adding together to create a larger net force.